So we just finished up talking about the three parent functions, the linear parent function, the absolute value, and the quadratic parent function. Now those are the basic graphs of each family, and they are positioned right at the origin in what's considered to be like the standard basic location. In this lesson, we're going to look at transforming those parent functions, moving them around in some way, or stretching them, or reflecting them, and making those changes that give us other members of the families of the linear graphs, absolute value graphs, and the quadratic graphs. We're going to look basically at the rules for transforming, and mainly we're going to apply it to the absolute value in this lesson, but certainly we will later on apply these same rules to transform other functions. So as we see here, a transformation changes the position or size of a figure, and transformations can be applied to parent functions. So let's recall the parent function for absolute value. So that's f of x is equal to the absolute value of x, and that graph had its vertex right there at the origin, and it looked basically like a V with a slope of 1 on one side and -1 on the other, and so we had these branches that created a V. So what we're going to do is to use our graphing calculator, and we're going to graph these new functions, these functions that have had something done to them, and we're going to compare it to the original parent function and see if we can give a brief description that might describe the transformation or change of position or size that is happening to the parent function. So for instance, number 1, the function is the absolute value of x plus 2. So I went ahead and graphed that along with the parent function on my calculator. If I had done it on the graph up here, the plus 2, remember that makes my vertex, whatever makes that 0, which is -2, so it would have its vertex at -2, 0, and then it would rise and run according to the same slope of 1, and so essentially we would get a graph that looks just like that original one, except for it is shifted over 2 units to the left. And you can clearly see how like every single point just went 2 units to the left, even the vertex 2 units to the left, points here 2 units to the left. And so if I wanted to describe what's actually happening in comparison to the parent graph, it is slid left 2. Now that's kind of funny because, I mean, when I look at this plus 2, if I add 2 to the x, I might think that's going to the right. And we're actually going to see that that is actually consistent to the rule for transforming by sliding horizontally. I actually even took a little picture of the graph of the parent in this new one on my graphing calculator, and here it is. And the red graph is the new function, and the blue graph is the original, the parent function, and you can see it looks just like my drawing up top. So we're going to be doing this with the graphing calculator instead of graphing this every time. On our paper, we're going to be looking on the graphing calculator, and we're going to compare and see if we can describe the transformation. So let's look at the next one. So x minus 2, you might kind of have a hypothesis about what's going to happen here, but let me go ahead and show you what the picture of that graph looked like. And comparing the parent graph, which is the blue one, to the new one, the red one, you can see that it looks exactly the same, but it was just slid to the right, and it looks like every point just moved 2 units. So I can see where that 2 comes from. By subtracting 2 from the x, we actually were sliding it 2 units to the right. Okay, how about the next one? Now this next one looks similar to number 1, with the exception that this plus 2 is actually outside the absolute value. So let's see how that affects things, see if it looks exactly the same as 1 or if there's something different going on. Here's a picture of what that looked like on the graphing calculator. Now notice on this one that the red graph, which is the new graph, is actually slid up. And if you look closely, you can see It slid up 2 units, which that's the significance of that plus 2 being outside the absolute value, not directly changing x inside the absolute value. This, in effect, just took the whole graph and slid it up 2. And so this was a slide up 2. So with that in mind, you might make a hypothesis about number 4, and maybe you think because it says minus 2 on the outside, it's going to move it down 2. So let's take a look at what that graph looks like. And sure enough, that is a slide down 2. So interestingly enough, when I actually added 2 inside, it moved it to the left, where I might anticipate adding 2 to the x would move it to the right 2 because it's a positive 2, but in fact it moved it to the left. And when I subtracted 2 directly from the x, it actually moved it to the right, which I would have anticipated it went the other way. But when the adding and subtracting was actually outside the absolute value, when it wasn't directly changing x, it actually behaved exactly what I might think. When I added 2, like in number 3, it slid the whole graph up 2, and when I subtracted 2 from absolute value of x, it actually moved it down 2. So what about in number 5? Say we took the absolute value of x, and we just multiplied the whole thing, that whole parent function, by 2. Let's take a look at the graph and see what happens to the function, the parent function, when we multiply it by 2. If you look at that red graph, which is again the new function, it looks like it's much steeper. And in fact, the reason for that is because this is a vertical stretch. It's basically taking any of the points on this parent graph and taking them and just like stretching them up so they're twice as far away from the x-axis. Like, for instance, here's a point right here on the original right there, and then twice as far up is a point on the new. And so it's just actually doubling the distance away from the x-axis. It's doing a vertical stretch. And so we could say this was stretched vertically by 2, by a factor of 2. And the reason why I would call it a vertical stretch is it's being stretched up away from the x-axis. So it's a vertical stretch and by a factor of 2. So we're just doubling the distance away from the x-axis for every single point to stretch it up. So with that knowledge, and if we thought about number 6, instead of multiplying by 2, we're taking the parent function and multiplying a half. You might think that it would have the opposite effect. So let's take a look and see what that calculator picture looks like. And that picture seems to confirm the hypothesis that instead of stretching it up and making it much skinnier and twice as tall, in fact, it's actually compressing it. It's actually pushing it down closer to the x-axis, and we actually call that a vertical compression. And that's because every single one of these points on the 2 graphs, except for, of course, the one at 0, 0, on the new function are half as far away from the x-axis as they were before. I mean, you can clearly see that this point was this far away, and now it's this far away. So it's only half that distance away from the x-axis. It's like something is up on top of the x-axis and on the bottom of the x-axis, and it's just pressing towards the middle, towards the x-axis, and just compressing the graph down, making it flatter. And that really is characteristic of a vertical compression. So it's compressing it vertically, so from top and bottom, compressing it back towards the x-axis. And how about this last one? So if we took the absolute value of x, that parent graph, but we put a negative out in front. Well, we've actually already talked about what the significance of that negative out in front is. It actually works to flip the absolute value graph down, facing downward. It doesn't affect the vertex, but instead of facing up, the v faces down. And so this is what the picture of that would look like on the calculator. And so clearly that actually is a reflection. So we're going to say that's a reflection. And if we want to be specific, which we need to be, we have to say what it's a reflection over. So it's a reflection over the x-axis. Because you can see here's the x-axis and the graph up top, which is the original parent function, its mirror image is below the x-axis now, pointing downward. So that's a reflection over the x-axis. Now, as it turns out, if that negative instead was inside the absolute value, in other words, if it looked like this instead, if it was with the negative inside, remember that absolute value brackets that is going to actually cancel out that negative. So if I were to instead have reflected this over the, or took the opposite of x, it would have reflected it over the y-axis, which would mean it wouldn't look any different, because what would happen is this this branch that's right here would go over on the other side and vice versa, and so it would just look like the exact same graph. So reflecting that over the y-axis would really, you wouldn't be able to discern that by just looking at the calculator. It would just look like the same graph, but right on top of the other. So let's go ahead and turn the page and take a look at the rules for transformations. Now, what's really great about these rules is that when we learn the rules for one family of functions, like we're looking at them for absolute value, we actually know those rules for any of the other families of functions we're going to study. The rules work exactly the same, and so we can always depend on them. Once we learn them, we come back to them each time we do any transformations. So in general, the transformation f of x plus h, we just saw one. The example we saw was when we did this. We took the absolute value of x and we added 2 to it. And remember so this is our little example. And what that did was a slide. And the direction was that kind of the opposite of what we thought. So when we added h, it actually slid it left. And I usually like to say that anything that changes in the x direction, and you'll see this is true for other things too, but it kind of lies to you, because it looks like when I added this 2 to the x in the absolute value brackets, it looked like it should have probably moved it to the right, but in fact it moved it to the left. And so that's how I kind of remember that's how it's going to behave when it's directly changing the x. In other words, it's, in this case, inside the absolute value brackets with it, it goes in the opposite direction I think is going to happen. So then looking at that next rule, f of x minus h, that actually is a slide and to the right this time. Now in both cases, it's h units. So we would say h is like the slide factor. So this one, the first one is a slide left h units, and the second one is a slide right h units. So it's still the same number of units. So remember when we looked at the one for the absolute value of x minus 2, and that one slid to the right instead of to the left as we might have anticipated. Now recall the example that looked like the next rule. We had the absolute value of x plus 2. And when we had one that looked like that, this was actually a slide up, or in other words, a vertical slide. And so it actually did what we thought it was going to do, which adding 2 you'd think would slide up, and it actually did. And so the significance of that is when it's not directly paired with x, in this case it's on the outside of the absolute value brackets, it behaves as we might think. And so this is a slide up. And this time they'll call it k units, and that's because so they use k for the rule when it's changing it vertically. So these, this one right here and the next one, these are both going to be vertical slides, and the top 2 are horizontal slides, so the ones that slide left or right. Now another word we use to describe that, instead of saying slide, sometimes we'll say translation. So I know that sounds like transformation, but translation is the slide, and you may remember that terminology from geometry. So following that same pattern then, if we had the example that we had that looks like this one, it was the absolute value of x minus 2. And so in this case, this would be a slide down, because I'm subtracting 2, and it's behaving what I think, because x lies to you, but y tells you the truth. So when we say that x lies to you, that's why they're your x. Just kind of a little joke to go along with that to help us remember that If they lie to you, they're going to be your X. So a slide, in this case, is a slide down. So the Y is telling us the truth, and it would slide down whatever that K value is, units. And so the vertical slides behave exactly what we'd anticipate, and the horizontal will go in the opposite direction that we might think. So that covers the slides, left and right, up and down. Let's take a look at the dilations. So though we'll look at some other dilations down the road, the dilations that we looked at in our sort of warm-up examples, we looked at dilations that affected the graph vertically. So these are vertical dilations. So what was happening is either we were stretching the graph vertically, so in other words, making it taller and skinnier. And again, relative to the x-axis, it was getting further away, like it's being stretched away, or a compression, which was being pushed back towards the x-axis, sort of flatten it out, but still it's a dilation. It's just flattening it out, making it smaller. And then the rules look like this. So they look identical when you look at the rule. There's no difference there. But when we look over next to it, the definition of how we defined A, in the first one, if A absolute value is greater than 1, so in other words, if we have something like 2 or 3 or 4 or whatever, that's going to cause us to have a stretch, so a vertical stretch, and it would be by a factor of A, so whatever that happened to be, if it was 3 or 4 or 5 or even 9/4, which is like larger than 1. So anything greater than 1 would cause a stretch. And if instead A was a number that's absolute value was less than 1, so things like a half or 3/4 or whatever, what that's going to cause is a vertical compression. And so when you think about the word compression, it's like we're pressing it down, compressing it, or like if you've heard of a trash compactor, like a compressor, and it's just pushing it back down towards the x-axis and really flattening it out but making it shorter. Now the example we happen to use was for the vertical stretch was absolute value of x times 2, or 2 times the absolute value of x, and that was one of those vertical stretches. And the compression example was when we multiplied the absolute value of x by a half, so then that compressed it back down. Now, as I said earlier, we will look at the dilations that would affect horizontally. So, but those kind of behave a little bit differently, and we're going to hold off to do those when we study another family of functions. But we're going to move on and talk about reflections. So there really are two types of reflections. The first one, we looked at an example, and the example we looked at was the absolute value, or the opposite of the absolute value of x. And that was the one that caused a reflection over the x-axis. Now that's predominantly the one that we're going to be focusing on in this lesson, is the reflection over the x-axis. And we talked about why that in most cases that would be, is because if we reflected over to a parent function, for instance, and reflected over the y-axis, because the v already is symmetric about that y-axis, you wouldn't even be able to see that there was a separate graph, or a different graph on another graph, excuse me. It's not a separate graph, it's the same graph, because it would one branch would reflect over to the right hand branch would reflect to the left side, and the left hand side to the right side, so it would just land right on top of itself. But with some other functions, you'll actually be able to pick up a reflection over the y-axis, so we are going to talk about the rule for it. And it is f of negative x. So the difference here is where the negative is. See how the negative this time is in with the x? And so anytime we go directly into a function and wherever the x is, we change this line directly on the x. The effect of that is going to be to reflect over the y-axis. And if you think about reflecting over the y-axis, if you move something from one side, say the right-hand side of the y-axis, to the left-hand side or whatever, you're actually moving its position horizontally. You're moving it from right to left or left to right. And so we actually would classify that as a vertical, no, it is a horizontal reflection, whereas the one over the x-axis is a vertical reflection, because so instead of facing up, you're facing down, so you're changing position vertically. And so you'll see that in that case, with the reflection of the y-axis, I'm going in and changing x directly. That's kind of how it worked with the slides left or right. We went in and directly changed x by adding or subtracting from the x. And in fact, it behaved in the opposite direction. But we'll get a chance to spend more time on reflections over the y-axis in later lessons. And this lesson will basically focus on reflections over the x-axis and basically taking our absolute value functions and making them face down. So that's really going to do it for just sort of the setup of the rules and our quick examples we looked at. The rest of our lesson will basically revolve around taking these rules and try to put them into practice. We'll also look at something called vertex form for absolute value graphs. So when we resume our lesson, that's where we'll pick up. So thanks for coming to class.